This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Podker. Plastics have historically been developed to be optimal for a specific use. But what if a single material could be made flexible for one application or sturdy for another? Our guest today is Stuart Rowan, the Barry L. McLean Professor for Molecular Engineering, Innovation, and Enterprise in the University of Chicago Pritzker School of Molecular Engineering, who is working to revolutionize the world of polymers by developing materials whose properties can be changed on demand. Professor Rowan, thank you for joining us today.
It's great to be here, Nate. Good to talk to you.
So I like to start with a little bit of the background, and I'm curious what first got you interested in chemistry?
I always kind of like to say that chemistry chose me because it was the only thing I was ever any good at in high school. And so when you're sort of good at something, you get more interested in it, and that's kind of what happened to me. And I just then fell in love with this idea of being able just to transform materials and understand how materials and things are transformed. And so that's how I got interested in chemistry. It picked me.
Then it goes and it gets more complicated, and you end up doing some of the crazy things we're going to talk about today that don't make sense to me at all.
Well, hopefully by the end of this, it will make sense, Nate.
Absolutely. But I think the bit that doesn't make sense is the ability to do the two things at once is really confusing for me. So one of the things we need to set up along the way is defining what a polymer is. And I know there's natural and synthetic polymers. So could you kind of explain what they are in general and then maybe the two varieties?
So a polymer is just a very, very big molecule. If it's a linear polymer, it's just, thousands of atoms stringed together. And the term polymer, it actually comes from the Greek, poly meaning many and meros meaning parts. So it's just a large molecule made of many, many parts. And so that's how to think about it. Maybe the best analogy of thinking about a polymer versus a small molecule is to think about cooked spaghetti versus like small macaroni, right? Where you've got this ability, the polymer, these very long polymer chains have this ability to entangle with each other like your cooked spaghetti does. And that gives polymers a lot of the properties that they have and makes them different from maybe smaller molecules.
Okay, so thinking about polymers and their use in the chemistry world, I guess, and maybe in plastics is kind of where my brain was going when I think of polymers. How have polymers generally been used to date?
Yeah, so polymers are used it touches almost every part of our daily life. So the clothes that I'm wearing, clothes that you're wearing, are made from polymers, right? Obviously the plastics that you see around yourself. Foams in your bed or car seats, these are polymers, right? Glues are to a large extent are polymers. So they touch so many different parts of our lives. Which polymer you use, dictates, the property. So there's better polymers that are used for fibers. Nylon, for example, very common polymer, and it makes really good fibers. Polyethylene terephthalate, which is really the Coke bottles or the bottles for your soda, right? That's a very different type of polymer, and it's really needed to help prevent the gas from getting out. So there's different properties for different polymers, and over the years, scientists have discovered a wide range of polymers, and they're really designed for specific applications, which is why, one of the challenges, right? We use so many different polymers. This makes recycling very challenging because we have to separate them out, right, before we can properly recycle the plastic.
Right, and I think that's skipping ahead a little bit. That was one of the things I wanted to ask you about. Is kind of historically, when you're designing polymers, you're kind of trying to get it best for one application. What are the benefits to having it be best at only one way?
And you can tailor, through chemistry and processing of the material, the properties to optimize for a given application, right? So that might be ideal. You need a different type of polymer if you're going to make a sweater like this versus the bottle I talked about. And they've been optimized to give you the best robustness. And generally, they historically we were always worried about degradation of polymers, i.e. they would degrade too quickly. So if you go back 50 years ago when scientists were really doing a lot of the sort of the growth work, we wanted plastics to last for as long as possible. We were too good at that design, right? That's clearly what we're seeing right now. And so now what needs to happen, because single-use plastics are really what's causing the problem. The plastic is cheap, so it makes it easier. They're lightweight, so it makes transport easier. And they're disposable, right? I mean, that's what we do. And that used to be a good thing, but look at what's happened because of that, people just throwing them away. That's now mean polymer scientists have to rethink, right? We all have to rethink. We need to be able to recycle this. We can't keep throwing away the plastics, which means that we need to, what we do want is we still want the properties of these optimized materials that we're used to using in our daily lives. We don't want to have to change what we normally do. We just want to have the materials to be, more easy to recycle. So we're not using just the single-use plastics extensively. So that's kind of maybe, that's really, sort of where polymer science is right now. How do we get those properties we're used to? How do we get better properties? We're always after that. But how do we make sure that we can make this more circular, right? That there's value in recycling the plastic and we're not just going to throw them in the oceans, which is obviously what we don't want to do.
Right. And maybe getting around the kind of properties that are making it so microplastics happen.
Yes.
Now, your work that kind of brought this conversation into being today is really with these pluripotent polymers. Can you kind of explain what that is and where did the idea of doing this come from?
So pluripotency is kind of defined in the dictionary as really is not defined as to developmental potentialities. That means it could be used for many different things. And really, I first, like most people, first come across the term pluripotency, if you've heard it before, in stem cells, right? So these are stem cells in the body that have the ability to turn into any cell in the body, right? That just to me is just a mind-blowing idea and concept. I just loved it. And so as a polymer chemist, I'm not a biologist, so as a polymer chemist, I thought, wouldn't it be cool if we can design one plastic, an undifferentiated plastic, if you like, that we could then turn into the bottle or the plastic fork or an adhesive or whatever. And that way, essentially, it's the same source of the material can be used for any of these types of plastics that we currently use today. That would do a number of different things, but one most obviously is we would, if all of our materials were made from one plastic, right? It makes recycling much easier because we don't need to sort them out, right? We can just collect the knives and the sweaters and the foams all together and just reprocess them. So the idea was kind of along those kind of lines, and it really all came from being rather jealous of the ability of stem cells, and why can't plastics do that?
So I guess I have to ask you about your magic trick here. Like, how did you do this?
So we've designed polymers and where the bonds are reversible, right? They can be broken and reform, right? And so we use a trick that that metallurgists have been using for years, right? Going back to, we get inspiration from wherever we can get inspiration. Biology gives us the idea. We're using a process called tempering. And so this has been used for blacksmiths since the middle centuries, where you essentially heat your material to a given temperature, and then you quench it. You quickly cool it down. Blacksmiths really discovered that this allowed you to expand the property profile of steel. If you do it, or iron, if you do it at very low temperatures, or lowish temperatures, the material is very stiff. Great for the edge of a knife, right? But if you were to make your sword out of that, it's very brittle too. So your sword would just shatter. So that's not very useful. And that's also not a useful property for armor. You don't want that one hit and your armor just falls to bits. So what they found out is if they heat it to much higher temperatures, the material was a little softer but much tougher. So it could withstand the blows, and this was perfect for armor. We're doing the same process, heating to a very given temperature and then cooling, quenching down. But we're doing it in a plastic, and such that we can essentially heat anywhere between 60 degrees Celsius and 100 degrees Celsius, right? So temperatures that are reasonably easily accessible. And if we heat the material to 60 degrees Celsius and cool it down quickly, it's very stiff. It's like a plastic spoon. But if you heat it up to 100 degrees and quickly quench it, now it's very soft. It's almost rubbery. So a very soft material. And this allowed us, and it keeps those properties for months. So this allowed us to start thinking about, normally if you wanted a stiff material, like a spoon, you'd need a very different plastic if you wanted to have that as the rubber, right? Now we can access that. And essentially all we're doing is the materials that we have are kind of cross-linked networks, right? So they're polymer chains, but instead of being linear, they're joined together. So you get this network structure, a molecular structure out. What we do during the tempering process is actually we control the number of cross-links between. So at low temperatures, we have lots of cross-links. That gives a very stiff material. At high temperatures, we have a lot fewer cross-links, and that gives a more rubbery, extensible material. And we can do that reversibly. So if we take that rubbery material and we just temper it at the lower temperature, we'll get back to the stiff material again. And so this now dramatically expands the property profile one material can get, and now allows us to use these in different applications.
And you can do this in one piece, right? Like
yes.
One end of it could be the more flexible end, and yes. One could be a more stiff end.
Yes, this is a process that the blacksmiths would call differential tempering, and it's actually really important for making swords, right? Because you want your edge to be very stiff, and the center needs to be tough. So they would how they make swords is they would differentially temper those swords, and so we're kind of again always being inspired by things that have gone before, and so this became a really that's kind of how we started looking. Can we actually differentially temper this and have one side being very stretchy and the other very stiff, as you say?
And now you talked about being able to go from one way to the other. With the recycling of it, can you turn it back to the base material?
Yes.
Like if you did the hot and then the cooler, could it?
Yes, it's completely
back and forth?
Yes, it's completely reversible, and we show that in the paper too, that we can cycle between these extremes, right, very easily. So it's very recyclable in that respect. And it, the other way that you can think about this, and we worked a little bit with both NASA and the Army research labs on this project, but you could think about this as being an interesting material for when you're in material scarce environments. Right. So if we happen to be on Mars, right, I always make the joke that there's no Walmart on Mars. So if you need an adhesive and you don't have any with you, what are you going to do? It's expensive to take stuff to Mars. So the idea is, let's take our pluripotent material to Mars, and then as you need it, you temper it. And if you need a spoon one day, right, to eat your soup, that's great. But the next day, maybe we need an adhesive. So we can just convert it into that. So I think thinking about this in resource scarce environments is another avenue where you might be able to utilize such a material, where you just take one batch of that material and turn it into what you need as you need it.
Right. It'd be a lot more valuable than bringing, I don't know, a truckload of wooden whatever. Like if you had like a suitcase worth of this stuff, let's say, you could make a lot of anything out of it.
Yeah.
This is very interesting. Thinking about the practical applications a little bit, what kind of uses did you see beyond that? Like what other uses could you see it being used?
So we focused in this first work really at changing the mechanical properties, right? And that's we show that we can use it as an adhesive. We actually show we can use it as an actuator, right? Like a polymeric muscle. And that we can also use it as essentially as making utensils. We show videos of all of these things. Right. What we need to do now is we want to try and expand the property profile. So that's a big challenge right now, so that we can maybe make milk jugs out of it, right? So can we get properties that are akin to polyethylene or polypropylene, the big commercial plastics out there? So we're working on that for this next generation. We need them to be a little tougher. So that's what we're working on. The applications in the long run could be anywhere where you see a plastic being used. We would like to have a material that could access any of those properties. That's a huge challenge, and we're not close to that right now. But what we've kind of shown is that we've kind of sort of proved the initial concept. Now we need to expand the property profiles. But beyond mechanical properties, polymers have are used in a wide range of other applications. There are polymers used in your batteries. And so polymers essentially controlling the ion conduction as separators between the electrodes. We're working on a material right now where we can control the ionic conductivity in the polymer through tempering. That's what we'd like. Can we control functional properties as well as mechanical properties? So those are the kind of things that we're trying to think about. Whatever a polymer is used, can we help to design a way where we can make a pluripotent version of that to allow it to be used for different types of applications?
Thinking about the strategy working towards those goals, do you have to introduce other kinds of material into that net to get these other kinds of functions out?
So yes, I mean that's what we're exploring right now. Different types of chemistry in the system. We're still trying to figure out. We designed this first material, and we have some ideas of what's important to make the material pluripotent. But we don't know all the rules yet. And that's another aspect. I mean, that's the kind of the fun aspect of this is like how far can we push this? And if we push it too far, how can then we evolve the system to allow us to go that extra further step to get other properties? We're looking at composite systems now. We're looking at more glassy materials now. And just thinking about how far we can push this idea and this concept. The way we did this is using reversible bonds. These are called dynamic bonds. But there's other ideas that I'm sure other people will come up with, but other ideas that we also have on different mechanisms or different approaches that we could to access the broader concept of pluripotency.
I'm backtracking a little bit because my brain caught up with this idea. When we were thinking about recycling it and thinking about it as a net, as you're moving back and forth with the tempering, does it break down over time? Like what would be the shelf life?
So I mean that's one of the we looked at how long if you temper the material, how long do the properties stay? Right before you might need to temper it again. Right, they will eventually revert back to an equilibrium state, like a standard state, but it takes months. Right, and what we did, one could imagine that you might want a pluripotent material where you do the tempering once and it's always that behavior, that would be nice, but it then inhibits the idea of retempering and doing the reverse. I always like to say, we train our bodies. And you have a different training protocol to maybe become a weightlifter versus a runner. Right. But of course, if we stop training, we lose that ability. And so and I think part of the reason why this is helpful is that we can maybe train 1 year to be a runner and then the next year to be a weightlifter. We have that ability, that adaptability that gives our bodies this kind of general idea of pluripotency. We can be refined and trained into these different abilities. Having it such that it is reversible, I think, is a really key component to be able, especially if you're in that resource scarce environment, or if we want to recycle it, we need to be able to easily break it down back into its components and then reform it again. If we can't do that, then we switch off that ability to do the recycling, which I think is an important component of this, and changing it into these different properties.
Right. So I want to ask you about something else that's not on this list that I came across when I was doing my research here. Like probably 10 years ago, you had the self-healing polymer. And I kind of was curious what happened with that, because it seems like that should be on every car I see right now.
So these I should say that these pluripotent materials also heal. Right, it's using a similar idea of these reversible bonds, so they also heal in addition to all of that. We had some conversations with companies. I mean, that particular demonstration of the material was more like we've demonstrated the concept, right? I think the specific monomer units or specific components probably weren't scalable or commercially viable. But using that concept, I think there's a lot of people and industry as well have been sort of exploring this idea of getting these materials to broader applications. There are still challenges there. There's a lot to be done in development once you've got the initial idea. I think that's one of the challenges we have for the pluripotent materials too, right? We've proved some of the concepts. Now, I have students thinking about how can we make this with more commercially viable materials, right? That now start us to think about how do we get these out. And so this is always the big sort of challenge. How do you get the technology out from a lab, right, in a university to an actual, where someone can buy it at CVS or Walmart or wherever, right? And we're years away from that for sure. But now as we're starting to unravel the rules for having a pluripotent material, one of the things we're keeping in mind is how can we make it more commercially viable, such that we do get it out so that it could be utilized.
Right, that challenge along the development path to scaling and widespread production.
Yeah.
Luckily, the trips to Mars, where this might be most useful, are also a few years out.
Yes. So we've got a little bit of time, right?
Yeah.
But the other thing is if it is a trip to Mars, we can charge a little bit more for it, right? Right? It could be seen as a really interesting stepping stone, right? Between being more commercially viable and utilized under very, very specific conditions.
Special thanks to Stuart Rowan. For the Discovery Files, I'm Nate Podker. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.